Hello everyone, this is Rafik Riyad. I welcome all of you to the Nano Connect webinar. Today I'm very happy to introduce Dr. Alex Margolin. Is a Chief Operating Officer of Nanomaterials. He earned his PhD degree in chemistry from the Weizmann Institute of Science. Dr. Margolin is a specialist in the synthesis of inorganic fullerene nanoparticles, chemical engineering and chemical processing, electron microscopy, and X-ray powder diffractometry. He has published 20 scientific papers and has multiple patents in the field of explosives and nanotechnology. Dr. Margolin is a perfect example of a scientist transition from academia to industry, promoting scientific innovations to a significant outcome used today in hundreds of applications worldwide. Dr. Margolin, please.
Great honor and responsibility for me to share the work of entire teams that work hard entire years. As Rafi mentioned, I'm working for Nanomaterials Limited. The company has been established back in 2002, but its history should be traced back to 1992, when Professor Reshevten and his co-workers found that late inorganic structures being synthesized at nanoscale tend themselves to fold into closed cage nanostructures. Actually, the way like carbon, graphene do. The best way to visualize it is, let's imagine that this is graphene sheet, mono sheet. Let's fold it and we'll receive a kind of nanotube or tubular structure. It's a way that is easily visualized how those structures can be synthesized, but the truth is a little bit more complex. Our materials are a little bit more complex than graphene sheet. When the graphene sheet has a layer of carbon atoms in its layer, in case of inorganic layered materials, the structure is complex, where we have a layer of metal sandwiched between two layers of atoms. In our particular case of tungsten disulfide, it says those are sulfurs. Probably this is the reason that carbon structures gave more support from both governments and researchers in their research, but we were among the groups that were studying and then commercializing the new family of inorganic fullerene-like tungsten disulfide and molybdenum disulfide, but we will more concentrate on tungsten disulfide particles. The traditional pictures of micrographs from a variety of electron microscope shows on the right inorganic nanotubes. Please note the flexibility of those structures. We'll discuss it a little bit more. Regarding the almost spherical nanoparticles, which are called basically inorganic fullerene-like, because to some analogy to carbon analogs. On the same, we see a nice representation showing that they're almost spherical, and on TM pictures, we see that the particles exhibit hollow core, which is important for major properties that we will discuss later. In 1995, Dr. Ishai Feldman, on the picture on the left, discovered the mechanism proposed and discovered the mechanism of formation for those particles, and gave actually the boost to the field, because we have received the necessary tool for repeatable synthesis of those particles, which resulted in the efforts of group of Professor Tanner and his collaborators in synthesis of material. From another side, the availability of particles of material gave possibility to other research groups to study their properties. And not only from scientific point of view, but from the point of view of future application in industry. Basically, as we discussed, the nearly spherical particles, spherical particles are small. They are submicron or nano-sized, and they're able to fill the cracks in the containing surfaces, contacting surfaces. Basically, when researchers saw these spherical particles, they saw about the possibility of using them like nano ball bearings. In addition, layered materials of tungsten disulfide, molybdenum disulfide are used, as well as graphite, as lubricating materials, as solid lubricants, as extreme pressure additives to lubricants. That's why the research in field of lubrication of that part of properties was in focus, and actually this grows up to a rise in our company. So as we mentioned, the spherical particles are able to penetrate to very small cracks due to their size and the shape. At some point, they roll between surfaces, thus lowering the friction. But it's less important that another effect that those particles are able to lower the wear. They serve as protecting barrier between two contacting surfaces and prevent the material to actually from material wear. The small size gives another remarkable feature that low amounts, low dosage of those materials are basically sufficient to reach the desired effectiveness, which is unbeatable with other analogs. Many researchers showed that friction and wear between contacting surfaces may be reduced up to 35–40%, depending on particular application. The hollow core that we discussed in the previous slide is of vital importance here because it helps particles to absorb shock. The study of behavior of individual particles under different pressures gave us some shade on mechanism of lubrication. Again, up to moderate pressures of, let's say, half gigapascal, the rolling effect, the rolling mechanism is prevailing. At some point, sliding is more typical for the particles, and at extreme pressures, the exfoliation or losing external layer took place, which actually leads to another remarkable feature of forming of protective layer of tungsten disulfide between contacting surfaces. There is a nice video of individual particle.
Due to their size and morphology, the nanoparticles fill the asperities and irregular surface of the metal gears, providing excellent load-bearing and anti-wear properties. Under high loads, layers peel from the fullerene-like spheres, forming a protective monolayer on metal surfaces, reducing wear and friction.
The main focus of company from its establishment was production scale-up to achieve the availability of particles in reasonable amounts. As a result, company designed, built, and launched, which was not so trivial, a series of setups. For instance, on the left, we see our former chief scientist, Professor Ala Zak, currently working in Holland Institute, with one of pilot setups. And on the right, we see industrial setup capable to produce up to quarter ton of material in a day. This is the company developed and introduced to the market variety of dispersions of particles in liquid carriers that actually serve the industry. Currently, we have a variety of solutions that serves in automotive industry, mining, agriculture, marine energy, everywhere that you have moving parts, but the most efficient those solutions are for heavy loads and high temperatures. One of the recent applications, our partners in Canada used the material in gearboxes of pump jack and reported of about 7% of energy consumption and operation of this pump, lower temperature of operation, and the most important, reduction in downtimes, which is very, very important for industry. Even more impressive numbers we may receive in power generation facilities based on diesel engines, used diesel engine oil to save on oil exchange, oil and maintenance up to 1.6 million per year. One of the recent developments that I want to mention today is water-based products, which are not typical for industry and can be used for metalworking. The metalworking requires good cooling, but requires lubrication. Up to now, some combinations of emulsions of oils in water were used, but it's it raises some questions from environmental point of view. Water itself is great coolant, but it's not lubricant at all. The combination of tungsten disulfide inorganic fullerene-like particles within water proved to be a high-performing lubricant fluid with extreme cooling properties, outstanding extreme pressure properties. It requires low treat rates, it's environment-friendly, and as a result, since it's oilless, it saves on disposal of used liquids. The company has developed already several additives for metalworking fluids that currently under testing at various locations all over the world that show remarkable properties. For instance, we may see a visual effect of surfaces under treatment with and without the particles, and the surfaces with the particles are more smooth, but the economic effect even more visible because our partners as industries, they try to evaluate everything in money. In this case, we can see that as a result of implementation of inorganic fullerene-like disulfide particles into metalworking fluids, water-based, we see a huge increase, around 80% of parts produced with the same tool, with maintenance cycle reduced from 3 down to 2. One of the remarkable points of those closed cage particles is their safe, which is certified by REACH registration certificate from European Community, which one of the strictest one in the world. We certified our activities according to highest ISO standards. And regarding the future, the elongated particles are often seen as a material for reinforcement. There are numerous works where nanotubes are used as fillers to composite materials, for instance, those results with polylactic acids. There are numerous works with other polymers as well. What is remarkable here is that we clearly see that increase of stress withstanding by the polymer with this composite material is reached at moderate concentrate of around 0.5%, while higher and lower concentration achieves lower results. It means that while working with nanomaterials, it is always necessary to find the optimum concentrations required for specific applications. It's kind of the challenge that this combination of academic and industry always should remember. Our international team is willing and foresee future applications of our particles, except for those that I was able to present in this short, limited time. And I mean, not only the team that currently is employed in the company, but entire teams that work, that participated in our activities. And I think that, thank you for your attention and thank you for providing this time to present somehow our activities.
Yes, Alex, there were a few questions to you, and if you go back and look into the questions, one question for you is similar to what I asked Barry. What would you do differently if you have to do it over again?
Very provocative question, and my nature cries me, won't join this company, but it's not right. I would do the same.
You do the same. Okay, thank you. I'm
really grateful to all those people that were in touch with me and worked together with me all this way. And the range of products we have is actually the joint effort of all this team.
Okay, thank you very much.